Hello and welcome to this recorded e-learning module for designers targeting Xilinx programmable FPGAs. My name is Srikanth and I will be your instructor for this module. In this module, we will learn about the basics of area constraints and their benefits. We will also learn how to make effective area constraints using the Plan Ahead tool. After completing this module, you will be able to create effective area constraints using Plan Ahead tool, identify floor planning methodologies, avoid the most common design and synthesis mistakes that make floor planning and gaining timing closure with the Plan Ahead tool. And you'll also learn how to place the dedicated hardware resources in the Plan Ahead tool. In ASIC world, floor planning means to place gates in a specific location in a gate array. This terminology has been borrowed by FPGA users, which means to place CLB logic in specific locations. As such, floor planning is not needed in an FPGA. But you can floor plan your design if it does not meet timing. Gate level floor planning is very difficult and time consuming. In FPGAs, floor planning improves timing by reducing routing delay without changing the gates in the design. But in fact, there are situations where certain timing problems are better solved by resynthesizing the netlist. As a general rule, engineers should floor plan hierarchy and not gates. Hierarchical floor planning is much easier as it serves as a guide to place and route of your logic. Xilinx does not discourage the use of area constraints. However, this does require some skill. The trick here for engineers is to first floor plan the timing critical logic hierarchy to a region on the device. This can be done after some chip and design analysis. This brings a certain level of repeatability to subsequent place and route runs even if the netlist changes. Sometimes it can be a good idea to floor plan some non-timing critical logic to get it out of the way of the timing critical logic. As a caution, whenever you hear the word floor plan, it's about area constraints, as these terms are still frequently confused. Floor planning may be considered when a design does not meet timing consistently, or when the design has never met timing. Floor planning has a much wider approach. It can range from more detailed approach, like such as placing individual logic elements of a critical path to a specific site on the chip, or the more abstract approach, like constraining levels of hierarchy to specific regions on the chip. Some design teams may spend time floor planning a design before the first iteration through place and route. Others may take a wait and see approach, electing to wait until a problem is identified before floor planning. Floor planning, if planned properly, can reduce routing congestion. You can use unique P-block capabilities in the Plan Ahead tool. We will discuss about P-block in the how to make area constraints with Plan Ahead REL. If you are going to use area constraints to improve your design speed or use partitions to maintain some of your results, here are some important recommendations which you can follow. Set up your synthesis tool to preserve the hierarchy in the netlist. This can be done by selecting the Keep Hierarchy option on in the synthesis options. Flattening your netlist may be optimal from a synthesis perspective, but they make it very difficult to reliably floor plan and constrain placement. If possible, try to structure your RTO logic so that critical timing paths are confined to individual modules. Note that critical paths that span large number of hierarchical modules can be difficult to floor plan. Try to register the outputs of all modules. This will help limit the number of modules involved in a critical path. You can also opt to replicate the drivers of nets that will be separated on the die. Synthesis may need an attribute to preserve logically equivalent logic. There may be some intermingled critical paths which can be very difficult to floor plan. You may consider dividing large critical blocks into smaller, and this will be very easier to isolate blocks. But if your design is expected to change very often, consider an incremental approach to synthesis. In an incremental approach, individual blocks can be synthesized separately, or synthesis attributes can be used to preserve the hierarchy. Hierarchy preservation helps an incremental flow, but may hurt your performance since global optimizations across hierarchy are disabled. You may need to consider the trade-off before you embark on any incremental RTL synthesis methodology. Constrain the synthesis engine to rebuild or otherwise preserve the hierarchy in the synthesized netlist. Flattening your netlist may be optimal from a synthesis perspective, but they will make it very difficult to reliably floor plan and constrain your placement. Consider using the synthesis option to rebuild the hierarchy. For XST, use netlist hierarchy is equal to rebuild. If using plan ahead tool for synthesis, the plan ahead default strategy includes this option. Long paths in single large hierarchical block can make floor planning a difficult task. Consider dividing large hierarchical blocks in the RTL. It will make it easy to work with smaller hierarchical blocks. Consider dividing large hierarchical blocks in the RTL, as it will be easy to work with smaller hierarchical blocks. The reuse flow can quickly help a design that meets timing only some of the time. The idea is to reuse some of the block RAM and DSP48 placement from a successful implementation run to seed a later run. This approach can be used when design meets timing some of the time and the names and structures for the macros do not change. Now you can synthesize this design and run the implementation tool as many times with only timing constraints and pin assignments. Then you can choose a result that has met timing and had the fastest implementation time. Try to fix the placement of block RAMs and DSP slices. And if required, try to re-implement the design. The hierarchical floor planning flow is more powerful than the reuse flow. A good hierarchical floor plan can close timing on a design that has never met timing. The analysis done to create a good floor plan can suggest design and logic changes to meet timing more easily and consistently. The hierarchical floor planning flow is resistant to design changes and can close timing and bring consistency to overall design. Synthesize the design and run implementation with only timing constraints and pin assignments. If it fails to meet timing, make the area constraints based on the highest level of your design hierarchy. In order to create a hierarchical floor plan, first synthesize the design. Then run the implementation with only timing constraints and pin assignments. If it fails to meet timing, make the area constraints based on the highest level of your design hierarchy. When you create a floor plan for your design, try to question yourself with the following. What are the timing failures in my design? Then what are the critical hierarchical blocks? And are these changes to the floor plan or critical logic going to be sufficient to meet timing? Or do I need to floor plan anything else? Can I just floor plan my critical hierarchy? And where should my logic be placed? Placing dedicated hardware such as block RAMs, DSP slices can be helpful in meeting the timing. But the implementation tools simply do not always do a good job in placing dedicated hardware. So this works well when you use area constraints. There are relatively few dedicated resources, so it will not take long to place some of these resources. Placement of dedicated resources guides the implementation tools to move CLB logic where you plan to put it. You should place the corresponding area constraints near the dedicated hardware you want to use. The dedicated resources will vary by device family. In general, designers are planning their device pin out early in the design cycle, and they are planning to use the pins nearest the dedicated hardware resources to minimize routing delay. This is equally important when you use area constraints to place CLB logic near your chosen pin assignments. This is equally important when you use area constraints to place CLB logic near your chosen pin assignments and dedicated hardware. The key dedicated hardware resources include clocking resources, block RAMs, DSP slices, high-speed serial transceivers, PCI interface blocks, dedicated memory controllers, and tri-mode Ethernet MACs. In Spartan 6 FPGA, the high-speed serial transceivers are located on the left edge. This is only available in LXT subfamily. The LX subfamily has regular I/O on the left edge of the die. Note that the Vertex 6 FPGA 5.4 logic is placed with the block RAM resources. You should be in the habit of making area constraints that make sense to the placement of your dedicated hardware. Also note that the placement of dedicated hardware varies considerably by device family and density. Area constraints that work for one device will need to be altered if the design will move to another device. When you assign LOC constraints to primitives, no DRC is performed. This means that you can accidentally break carry chains and other design rules. Be aware of any placement restrictions when you are assigning LOCs to primitives. You can place a leaf-level primitive instance into a specific device resource site by dragging it from the netlist tree and dropping it onto a specific site. When you place instances into sites, plan ahead adds instance location constraints to exported UCF files for ASC. The assigned locations are assigned as fixed and locked during subsequent ISC attempts. Most logic objects can be manually assigned to a specific site. Click the Create Site Constraints Mode toolbar button. Note that placed logic has a blue bar. Logic is easily found with a find command and then dragged to be placed. Cursor indicates legal placement sites and right-click allows you to unplace. The basic element constraints, abbreviated as BEL, is an advanced placement constraints. BEL locks a logical symbol to a particular BEL site in a slice or an IOP. BEL differs from location or LOC in that LOC allows specifications to the component level. Examples of components are slices, block RAMs, InLogics, OLogics, and IOPs. BEL allows specification as to which particular BEL site of the component is to be used. BEL allows specification as to which particular BEL site of the component to be used. For example, this can be used to specify the specific LUT or flip-flops to be used within a slice. Click the Create BEL Constraint Mode toolbar button. Drag a LUT or flip-flop primitive from the Find menu or netlist view onto a specific slice. Primitive with LOC constraints are displayed in the netlist view with blue striped icons. Click the Assign Instance Mode toolbar button to return to the floor planning mode. Instance location constraints can be selectively removed from the design. You can filter the type of constraints you want to clear based on the ISC assigned, selected logic, or P-blocks and specific logic types. Pre-selected objects will dictate the behavior of the Clear Placement Constraints wizard. If P-blocks are pre-selected, the wizard displays default settings to clear placement constraints inside of them. The tool has a concept of fixed versus unfixed logic. You will want to place some objects like IOs, block RAMs, for example, onto these LOCs and are considered fixed. For analyzing place and route timing, it is useful to see where the implementation tools place these objects. For the tools to do this, their placements must be unfixed. Before exporting the placement for an implementation run or to your UCF, the tool will ask if you want a LOC constraint in the UCF for all gates or just the user place fixed logic. In summary, to create an area constraint, use the timing report to identify logic to floor plan. Leverage the implementation results to guide placement of area constraints. Placement of dedicated resources can guide the implementation tools. Be sure to make an area constraint with the associated logic and assign it near the dedicated hardware to improve performance. Placement improves implementation consistency between each iteration.